Hi, here we are discussing about a project hybrid approximate multiplier with a merits balance for digital signal processing and neural network. In applications of digital signal processing, image processing and neural network escalation widely rely on high-speed multiplications where approximate computing has emerged as an effective approach to improve their energy efficiency and throughput. Okay, so here the approximate multiplier offers a clear advantage in terms of reduced power consumption, smaller area and faster operations. However, they also introduced challenges such as unbalanced error distributions, increased latency in accumulation stages and performance degradations due to inefficient adder stitches. The primary problems addressed in this work is the delay and hardware complexity caused by conventional adders used in hybrid approximate multiplier architecture, which limits their effectiveness on FPGA platform. The existing approaches mainly focus on the approximation at the arithmetic level, such as a logarithmic or partial product based design, but often neglect optimized of the carry propagations and accumulations logic, by resulting in suboptimal delay and power performance. To overcome these limitations, this work proposes a hybrid approximate multiplier architectures that integrate a carry select adder implementations using a hexamux based full adder to reduce the carry propagation delay and the overall circuit complexity. The key novelty of the proposed designs lies in the combining the approximations over multiplications with a low latency and hardware efficiency adder structure, and it's enabling improved speed without significantly affecting a computational accuracy. The proposed architecture supports a signed arithmetic operations and is well suited for error-tolerant applications in FPGA-based systems. So this design is described using Verilog HDL and functional verified in modelism and synthesized on Xilinx Vertex 5 FPGA platform, and this design performs the evaluations in carried out in terms of lookup table utilization, slice registers, critical path delay and power consumption, and it's demonstrating noticeable improvement over existing hybrid approximate multiplier design and thereby ensuring enhanced performance, energy efficiency and reliable operation. Now we can verify the paper. So this paper is designed for fully approximate multiplier with the piecewise linear method. Here, what is piecewise linear method? The piecewise linear method is an approximate technique where a complex and non-linear functions it is divided into several small regions, and each region is approximated using a simple straight line equations instead of one complicated formula. In hardware, so this is very useful because the straight line can be implemented with using adders or shifters instead of a full multiplier. Okay, so which greatly reduce the power and area and delay. In this paper, the PWL is used in approximate the mantissa multiplication so that acceptable accuracy is maintained while making the circuit much more hardware efficient. Okay, so here in this paper they proved the architecture wise. Okay, so this is the architecture. It will shown in figure 3. Okay, so computational flow and the circuit diagram of the proposed multiplier with a hybrid logarithmic and specific mixed PWL processing. Okay, so here you can verify this architecture. So it will be present with ME, LOD, EMC and adders and mixed PWL architecture. Here ME is magnitude extractions. The operation of this ME is to find the signed bit, and if the signed bit is a negative, okay, so it will split the MSB and LSB, and LSB it will be using for 2's complement, and the MSB only it will be used for 1's complement purpose. Okay, so that is the operation of the ME architecture. And exponent magnitude conversions. Okay, so it will convert the magnitude value as per the LOD. Okay, so here the LOD is the main target of this work. So LOD it will protect the leading bit. Okay, so here we are given the 15 input bit. Okay, and we need to find the leading bit, and that bit log value it will be generated, and that value, it will be given to the EMC operations. Okay, so using this log value, the EMC, it will decide the shifting process of the magnitude conversions. Okay, after that it will split the value, which is the exponent and also for mantissa. Okay, so exponent it will be mentioned in EA and mantissa it will be mentioned in FA and FB. Okay, so here the FA and FB only it will be given to the mixed piecewise linear method. Okay, so this is the approximation part it will be used. Okay, so here this architectures, it's a core of PWL. Okay, so it will be come with the additions and the OR gate and multiplexer shift component and 3:2 compressors based additions. Okay, and finally it will produce the n value. Okay, that will be MTS. Okay, so which means a magnitude to signed conversions. Okay, so it will again direct the sign bit. Okay, and it will be invert the data, and the shifting unit will shift the data to the multiplexer output for 32-bit value. Okay, so this is a core of this work. So here it will become with more number of addition logics. Okay, so for proposed designs we used the XOR based carry select adder to reduce the logic size. Okay, so for that we used this paper, the implementations of XOR based 16-bit carry select adder for area, delay and power consumptions. Okay, so here this is a conventional design of the full adders and this is the XOR mux design of the full adder. So compared to these two architectures, the XOR mux it will be take only 2 logic gates and 1 multiplexer, and this designs it will be present with a carry select adder. Okay, so we designed the same core, but the architectures it will be customizable with a 4-bit and 6-bit and 8-bit architecture. So that architectures only it will be used here. Okay, so why? Because the EA additions it will become with a 4-bit. Okay, and mantissa additions it will become with a 6-bit. Okay, so as per that we customized the architectures and then we used it. Okay, so this work we have developed in Verilog HDL and simulated in Modelism and synthesized in Xilinx Vertex 5 FPGA and compared all the terms of area, power, delay. Okay, so now we will verify the work in Verilog HDL. Here you can verify the Verilog HDL coding for the top model architecture of hybrid approximate multiplier, and this is a proposed architecture. Okay, so proposed hybrid approximate multiplier architectures. So here simply the changes is RCA ripple carry adder it will be generated with the XOR based full adder design. Okay, with CSLA architecture. Okay, and this architecture's simulations it will be shown here. So input and input A and B and data check, data output value. So here the data check value is the exact value of the multiplication and data out is the approximate value of the multiplications. Okay, so here you can verify the all the output and approximations value. Okay, and this is a proposed one. Okay, so here you can verify the approximate value and accurate value of the multiplications. Okay, so this two works we have compared in error terms calculations. Okay, so which means it will become with the MED, NMED, MRED and error rate. Okay, so it will be calculated in every 50th iterations. Okay, so this is a MED, NMED, MRED, error rate values. Okay, and this work we synthesized in Xilinx Vertex 5 FPGA. So this is a conventional design. It will take for 369 LUT and occupied slices 173 and IOB equal to 64. And this is a proposed designs. Here we have reduced the LUT slice. It will become with a 320 and occupied slices 132 and IOB equal to 64. And here you can verify the RTL schematic of this work. Okay, so this is a proposed hybrid approximate multiplier. Okay, so it will be present with magnitude extraction, leading one directions, magnitude leading, and mixed PWL, exponent mantissa conversion, and exponent mantissa conversion with CSLA and shift unit. Okay, and this is a mixed PWL architecture. Okay, and This one is a comparisons. Okay, so existing and proposed comparisons. Okay, and we have written abstract document for this project. Title, base paper abstract, improvement and proposed title, proposed abstract. Okay, and related notes for this project. Okay, existing, proposed, disadvantages, advantages. Okay, everything we included. Okay, finally we come up with the literature review and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.
Introducing NXFE Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking, we offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At NXFE, you not only get expert-guided projects starting from RIS 6000 Rasparis, but also enjoy unmatched benefits like RIS 1000 off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on NXFE for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option, allowing you to pay module by module. Let NXFE guide you through your research journey with flexibility and expert support. Thank you.